reliable solar energy. So we are looking to make solar energy affordable and accessible for all Americans, support a reliable, resilient, and secure power grid, and also creating a sustainable energy industry that supports U.S. jobs, U.S. manufacturing, and a circular economy, so recycling and repowering of these systems. So my goal for the talk today is to, so maybe what I should really emphasize on that is that we're an applied research office, right? So we're not a policy office. We're not really out here trying to set tax policies or zoning rules or things like this, but we're really trying to understand and develop the technology that's out there. So I'm going to start by giving a little bit of context on where we are in solar energy in the U.S. today and some of the future scenarios we're laying out. So you may have seen a few weeks ago, DOE put out this big solar roadmap that runs out to 2050. I'm going to talk a little bit about that. There are some land use impacts that we see in those scenarios that we want to get ahead of if possible. I'm then going to talk a little bit about some of our programs relating to integrating solar with agriculture. And I'm kind of going to do this in two phases. The first is sort of speaking in generalities about some of the possible technologies and open questions that we have seen or are looking at, know about, that are out there on the market and being tried in the US and around the world today. I would say there's actually probably more international activity than there is US activity in this area right now. Then I'm going to go through current projects. So CEDO has a number of actively funded projects right now that are working on solar plus agriculture combinations. And then I'm going to talk a little bit about opportunities to engage with our office or with some of our projects. And I'll be happy to answer questions at the end of the chat. Although if there's anything really, really critical, please don't hesitate to interrupt me if I've gone off the rails or you fear that there's something that really hampers the ability of the rest of the talk to be understood. So the story of the U.S. solar industry in the last 2 years is two things that are very clearly connected. The cost of solar has gone way down in the last decade, falling 80 or 90%, largely as hardware costs have declined and the economies of scale have really picked up. Meanwhile, the efficiency of panels has gone up. So when you think about the cost and how we usually measure them, which is cents per kilowatt hour, basically the amount of energy you've gotten for the same cost has gone way up. And the natural flip side of that is that the amount of solar that's been deployed is growing and growing. So I think the slide can actually update it with this year's data or so, maybe about now. But total solar installed capacity in the US is now at 95 gigawatts at the end of 2020. You can see in 2010 it was, I don't even know how to read that number. It might be 1 or 2. And the pace of deployment is still continuing to accelerate. We're looking to add, this looks like it's projecting 23 gigawatts by the end of the year, so 25% annual growth rate. And this rate of growth is not only expected to increase, but sort of needs to increase if we're going to deploy enough clean energy to meet the administration's climate goals. So in 2021, we put out this study called the Solar Future Study, which is really meant to chart a pathway to how can solar become like the keystone of a clean energy system, and particularly electricity grid, by 2050. So in the Solar Future Study, some of the aggressive targets look at 45% of US electricity coming from solar in 2050, a number that currently stands at about 3%. And the key thing here is it's all hinged around achieving like 95% decarbonization of the electricity grid by 2035. So we have a few different scenarios. There's 3 main ones. One is reference. This is kind of our business as usual case. And what I want to point out is that between 2020 and 2035, in the business as usual case, we're still seeing like an increase of 5x in the amount of solar that's out there. Then we have a decarb case. This is just a case that looks at decarbonizing the grid. So that about doubles the amount of solar you see if you say as a constraint, we need to hit 95% decarbonization by 2035. And finally, decarb plus E, which is the E stands for electrification. So this is what if we decarbonize the grid and we like electrify all the cars or as many of the cars as we can, switch gas heating to heat pumps and things like that. And so that there's just more electricity demand. And you can see that again pushes up the amount of solar we have to about 1,000 gigawatts or 1 terawatt by 2035. That leads to a lot of land use. So the estimates of land use used in the study are about 7.5 acres per megawatt. That's necessarily quite rough. In reality, it's going to vary by latitude, the type of hardware you have deployed, and things like that. But in the most aggressive scenario, by 2035, you're looking at about 5.7 million acres used for utility scale solar energy, going up to as much as 10 million acres in 2050. So the 2035 number would have come out to about 0.3% of US land area. rising to 0.5% in these kind of 2050 numbers. So for whatever reason, the person who made this figure decided Maryland was a good benchmark. So you can think of it as around a Maryland of land, which Maryland's not a huge state, but it's still stark how much it really is. So this is one of those numbers that is worth thinking about. I think the solar industry, in my experience, likes to play up the fact that 0.3% doesn't sound like very much, but 6 million acres is a lot of land, no matter what. And it is a fact that the land that works very well for solar energy is moderate climates and lots of sun. And so there's kind of a natural, because it's going to be a natural way in which this kind of overlaps with or has some intersection with agricultural land uses. So this is why we're interested in, I mean, there's various ways to address this problem, right? And I should say that I don't want to give the impression that we assume that all of this is just going to be deployed in concert with agrivoltaic or in concert with agriculture. We can develop solar on like former industrial sites or contaminated lands. We can encourage rooftop solar over utility scale solar. But of course, we kind of want every tool in the arsenal. We don't want to rule anything out. So one thing we're really interested in my office is this concept called agrivoltaics, which you can see is kind of trying to harvest the sun twice. So if we look at traditional solar development, and this is kind of what you would get if you had the sort of most basic kind of optimized for solar energy, don't worry about anything else. You would remove all the existing vegetation, you would strip and grade the topsoil on the site. You wouldn't try to have habitat for insects or birds or other animals. You would really just focus, I'd say, I don't want to have to manage vegetation. If plants grow under my panels, they could shade the panels, cut the production down. I don't want to deal with that. I'm going to spray a bunch of herbicide. I'm going to plant turf grass or something. So anyway, this is how a lot of traditional solar development has been done in the past. And I don't want to shame anyone for doing it. I mean, there's lots of development that tears up existing vegetation. But the question is, for solar, can we do better? Because we don't need to do all this stuff necessarily to still have productive solar facilities. So agrivoltaics, I keep using this word, I should probably actually define it. So for us, agrivoltaics is the combination of solar energy production with either pollinator habitat, livestock, or crop production on the same land. And so I really like to highlight on the same land because one thing that's also very interesting is a solar in kind of a rural context, where maybe you have an acre of solar farm, and then next to that you have some cultivation, and maybe it's being used for on-farm energy usage. That's great, but we're really trying to push the envelope and say, what can we accomplish by actually integrating these systems together? Because that's kind of where the technical frontier is, right? I mean, we know how to build solar, and then next to it build something else. This is what I'm really going to focus on here, is how do we build something that works together. There's kind of been a vocabulary struggle, I think, in what to call this. I've seen it called co-location of solar plus ag. I've seen it called dual use solar. I've seen it called ag PV or agrophotovoltaics. We've kind of settled on agrivoltaics in our office. There's a big international conference that's been hosted in Europe the last couple of years. It's just called Agrovoltaics. So that's kind of where we're landing, and that's the term I'll be using for the rest of this discussion. Okay, so I wrote this down into a few different things. So pollinators, the idea with pollinator habitat is that we can plant flowers, or grasses, or whatever, which intentionally support pollinators, insects, or birds. About 23% of U.S. crops depend on animals for pollination, and the hope is that if you have solar fields with pollinators, you can provide significant benefits to surrounding communities. So this map down here in the bottom right is showing how much agriculture in hectares is within 1.5 kilometers of solar facilities, and it's highly dependent on pollinators. So there's quite a bit in California, there's quite a bit in Massachusetts, and there's quite a bit in North Carolina. And part of that is just those are where big solar markets are, but I think that really starts to highlight the potential for quantifying and really understanding what is this benefit that's being provided and what kinds of pollination can we support. And there's at least one company out there that will sell you solar honey that does beekeeping in conjunction with kind of pollinator-friendly solar habitat. So the next broad category is grazing. So here, this is really kind of a dual use situation. So solar field needs vegetation management, right? I mean, I was just saying this is a big problem. They'd really like to keep their vegetation down. Usually that's herbicides plus mowing, but there are some sites out there, and there are some people out there who will come and bring their sheep and let the sheep manage the vegetation to some degree. Often this isn't 100%. You still need maybe someone who comes in with a weed eater or some light mowing to clean up, but it can really potentially, we hope, reduce the cost and effort involved in operations and maintenance, while meanwhile keeping the land still in cultivation and supporting sheep grazing. So this one is really interesting because while the pollinator habitat is really pushed a lot by local governments and state governments that are looking to encourage friendlier practices. The grazing, I think, has not received so much policy support, but there's already an industry association, the American Solar Grazing Association. I believe they're most active in New York State, but they're really working to promote this and network grazers together who can bring, mostly, again, at this point, sheep. The basic rule of thumb I've been told is that sheep are good because cattle are too large and might damage the panels, although we'll talk about a cattle project in a minute, and goats are too rambunctious and will jump all over everything. So sheep are the nice, the solar friendliest livestock at the moment. And then finally, crops, which I think are one of the more exciting areas, but definitely one of the ones that requires the most careful attention. So we're seeing kind of research type sites. This one on the top and the left is a place called Jack's Solar Garden in Colorado. And then this one on the bottom right, I believe, is the University of Massachusetts at Amherst, where it looks like this woman is maybe working with kale or broccoli or something. So, you know, you really have to, obviously you're competing for the same light source here. So you kind of have to ask yourself, for the crops I'm growing, you know, how light dependent is it? Can it survive at lower light levels? Can it, you know, and, you know, not just survive, but can I get economical yields out of it? Does it grow very tall? I don't want to grow anything that is going to block my production because of the way the sort of electrical nature of solar systems work. If you block production even a little bit, it can lower the production on the whole panel. So you really don't want to have any shading if you can avoid it. And then finally, can you hand harvest it, right? So I mean, you look at these things, yes, this man is on a tractor, but you're not going to get a huge combine through here. And so for that reason, we've really focused more on the tomatoes and peppers and specialty crops of the world and less on the corn, wheat, soybeans, important as those are, obviously. And then from the solar side, you have to ask yourself questions like, how are the panels spaced? So you look on the right here, you see these panels have big gaps in between, so that's to let more light through. And then are they high enough? And also, you know, they're up high so that workers can get in below here, as well as so that the crops can grow. Whereas if it were purely solar and no crop production, you might bunch these things as far together as you could, keep them, you know, low to the ground, because you're spending a lot of money on steel to raise these things up. So all these systems, these crop systems, I would say, are really high interest to us because we recognize this is where a lot of the land conflict could be. But there's a lot of open scientific questions that we're still trying to address. So, you know, for farmers, we see this as a potential to get into diversified revenue streams, potentially to have shading to mitigate heat stress for animals and crops, with attendant potential water savings. If you're doing pollinators, perhaps there's pollination services for agriculture nearby. And then finally, we're also thinking about on-farm energy production, especially from like a resilience point of view. Can we provide electricity that might be especially useful in remote areas where the grid is not as strong or is more prone to outages? And some of that is about us also trying to figure out where are the on-farm energy uses that most benefit from that kind of guarantee, and how much, for instance, battery storage would you need to guarantee that you can keep, let's say, incubators running, or water pumps or something like that. So here's an example from the University of Arizona where they were comparing crop growth under PV and in open control. So the PV shaded condition actually yielded more peppers, more tomatoes. You can see this graph is in total food production. I guess I don't know what the actual unit is here. More tomatoes, more peppers, a little bit less jalapeno, but not very much less. And actually the PV, the case underneath the photovoltaics, required between 30 and 50% less water. So, you know, especially I think in the Southwest region where we see significant heat stress on crops, this is a potentially very viable way to reduce that heat stress and maintain yields or even improve yields. But again, this was very climate specific. As you can see, it's also very crop specific, the different outputs and gains you get. So these are the kinds of questions that really need to be nailed down. Further plots here, the blue line here is soil moisture in the agrivoltaics case, where the red line is soil moisture over time. In the control case, you can see the moisture dips much lower in the control. And then this was the surface temperature difference was sort of varied throughout the day, obviously, but was consistently down by 5 or 10 degrees C lower. From a solar point of view, there's also benefits. So I want to emphasize we're really hoping this can be a two-way street. On one hand, there's the efficient vegetation management. I've kind of talked about that a couple of times, whether it's sheep or whether it's cultivation. You have someone paying attention to what the vegetation is doing here and sort of actively managing it. The other thing is a better microclimate. So transpiration from plants can promote cooler temperatures underneath the panels. And for solar panels, the efficiency of the panel actually goes down as the temperature rises. So cooler panels are produce more energy, and that can be quite lucrative, actually. And then finally, siting in partnership with local communities. So this one, I'm not going to say that we have good data on, but we know that there are agricultural communities or rural communities out there that are concerned about losing agricultural land to energy production. And it is our hope that this kind of technology and these kinds of development patterns can lead to sort of more land use that is more in harmony with local cultures and local communities, which I understand. I grew up on a small ranch in Oklahoma, and certainly I understand the ways that these kinds of practices are sort of bound up in people's notions of what their community is and what it does. And we want to avoid interfering with that as much as possible. So, like I said, there's also open questions here about long-term impacts on soil quality, what crops and where are really best suited for this kind of production, how you co-optimize system designs. We've spent years and years trying to learn how to design solar systems so that they're like where they squeeze every last drop of sunlight out of there. We don't know quite as much about how we do it for combined ag and energy yield, animal interactions. And then finally, I think a big question is, what are the actual contracts going to look like here? How do you assign revenue from the solar plant? Who pays these upfront capital costs? Questions like that, which I think are really interesting and need to be explored more to make sure that these are really maximally beneficial for the producer. So I'm going to take us on a quick tour through some of our agrivoltaics projects. Our flagship one is one called Inspire, which is hosted at the National Renewable Energy Laboratory. And they've been running for a couple cycles now, a couple funding cycles. So they're about to start their third 3-year grant. And they've really worked to build out a network of research sites, companies, and universities that are interested in agrivoltaics, as well as things that are not quite agrivoltaics, like the use of native vegetation and just general site preparation questions that go beyond that kind of traditional model of strip and grade that I mentioned earlier. So in Inspire 2.0, which is the one that just finished, they did field research at a number of sites across the country. You can see that Arizona site earlier. They also did some analytical studies trying to quantify these questions like, well, how much money do we save by doing solar grazing, for instance? Or what would it take to turn it into something that saves money if it doesn't at the moment? They're also really working to build this working group called Astro, which stands for Agriculture and Solar Together Research Opportunities. That is an expert advisory group, and it provides them a lot of feedback on their directions. And then finally, they're working to build out a website that will actually bring everything together into a unified data and information portal. In Inspire 3, we're really looking to go from research projects to scale to some degree. So they're just getting started, I guess, this week, basically. And you can see that their funding went up. It was 1.9 million for the last cycle, and now it's about 3.8. So they've nearly doubled. We're nearly doubling their funding for the next cycle, and they're going to be dramatically doing a lot of really great work, I think. So they're going to be maintaining this network. They're going to be starting to fund seed projects, so a few $1,000 grants to early career researchers and students. They also have money set aside for interagency collaboration. In their project plan, it says that they're going to be working to identify opportunities to work with NSF or USDA, Department of Interior. So if you hear something that I'm talking about that you think, oh, I'd love to work with DOE on that thing, well, our main project, the National Labs, has money set aside for just that. They're going to continue building out these kind of foundational questions. So establishing a database of sites and starting to track these things. You know, the time is kind of receding into the rearview mirror when we would just like know them all off the top of our head because there were only a couple. So we really want to be able to track these across the US and understand what's the rate of growth looking like. They're going to do a research needs assessment and try to lay out a roadmap for agrivoltaics research in the US and doing a lot of economic analysis. You know, so we've done this for small research sites. What does it look like in a multi-megawatt installation? And what kind of, how do the costs kind of change and compare to a traditional site? They're also going to do a bunch of field work in at least 7 states. They're also going to be working with a few tribes, I believe the Navajo Nation and another one in Nevada that I can't remember the name of, that they're going to be working with them to look at agrivoltaics for sort of traditional foodways. And the goal there is to really, you know, continue finding and recommending these alternate systems. They'll be trying to quantify the pollinator benefits and looking at some of the soil science impacts and conservation impacts that I mentioned. We don't really know right now. I think it looks like I'm about almost coming up on 25 minutes, so I don't want to take too much longer here. But the other main clump of projects I'm going to talk to are not at the national labs, or the national labs are at best only partners on them. And this is something we funded through a funding opportunity that we released in 2020. And it's really about, it was really seeking private individuals or organizations that might be interested in doing some research on co-located solar and agriculture. This is, I think, before we really come around to calling it agrivoltaics, so that's the language used here. We made 4 awards that came out to about $7 million total, and each award is going to last about 3 years. The University of Massachusetts at Amherst has a clean energy extension office that's really going to be working to study agrivoltaics across the state in a number of different crops: hay, cranberries, blueberries, grazing. Massachusetts actually has a lot of incentives in place for non-traditional solar siting. You know, they're sort of a smaller state, and so a little more land constrained. So they're already really working to encourage development on non-traditional sites. And so those incentives are driving a lot of interest from the private sector in that state. So UMass Amherst has a number of partner sites they're going to be working with, and they're also going to be conducting economic analysis to try to figure out, well, what does this do for farm profitability? What does that do for the economy that surrounds the farm? And understand what that means to neighbors and how communities are interacting with these installations. Silicon Ranch in Georgia is a regenerative agriculture company that does sheep and cattle grazing. They've done sheep grazing sites across the Southeast. Obviously, Americans eat a lot more cattle than they eat sheep, and so there's a lot of interest in building out the science of cattle-specific agrivoltaics. So they're working to engineer a field that will be sort of compatible with the cattle from an animal welfare point of view. They're also going to monitor the soil to try to understand the carbon impacts and bring in a lot of ranchers from across the country to understand a little bit better what the opportunity looks like here. The University of Illinois at Chicago is really going to look at pollinator plantings at large-scale solar facilities. So again, this is kind of part of our moving from research sites to large-scale facilities. So where we started at smaller sites and pollinator testing, lots of states are now starting to require or thinking about requiring pollinator habitat, even on very large facilities. And so they're going to be looking at very big sites, so 10 megawatts or larger, across the Midwest, and they're really going to be trying to build out things like cost-benefit calculations, seed mix analysis to try to determine what the best seed mixes for different soil types and environments are, and what the impacts are on the PV management and operational costs. And then finally, kind of tying it all together, the National Center for Appropriate Technologies is running what's called the Agri-Solar Clearinghouse, and this is really focused on information sharing. So they're building a website that will be supporting people to kind of conduct peer exchange of information and really start to lay down a professional network of people who are working in this space, who can learn more about what are the financing options or the tax incentives, how do the ownership structures work. They're going to build out technical assistance for individual producers who might be interested in working with this, host field trips to demonstration sites, and produce, I think, podcasts, videos, field guides, and things like this. So this is really, I was really excited we did this. We were looking over our applications, and we really thought this one was an opportunity to build something out that would be, that would really make all the other research count for much more, because it would get it in the hands of people who need it. I can't talk in detail about our FCIR funding, and not because it's secret, just because I don't work on our FCIR team, but we've also funded a lot of research that has agricultural relevance in FCIR. So solar culture, for instance, is greenhouse integration. Some of these others are alternative racking schemes, so different ways to mount the solar so that it's either less, has less interference to agricultural practices, or can be moved around more easily, or things like that. So I'm happy to discuss these more if people want, but I don't have deep knowledge of these projects the same way that I do for our more research-focused groups. So before I wrap up, I just want to throw in a couple opportunities we have for people to engage. So there's this Inspire Astro group. They do quarterly meetings where they present on everything that Astro has been doing. They update everyone on the Inspire project's research activities, and they try to coordinate outreach, press releases, and things like that. And as you can see, it kind of includes agricultural groups, research organizations, the solar industry, some state actors, and environmental organizations as well. This one's maybe not super relevant to this crowd, but if you know anyone who's interested in pursuing a little bit of a jaunt to the Department of Energy, this ORISE fellowship is one way that we bring on people for short 1 or 2 year appointments. This is how I originally joined the department, actually, really often focused on new graduates. So if you know anyone who's graduating in sort of the food energy space who you think might be interested in working in our office, please feel free to point them to this. Our office has a newsletter that updates people on our recent funding, publications from funded projects, key activities we're up to, that I encourage people to sign up for if they're interested in keeping up with what CETO is up to. And I think that brings me to the end of it. So yeah, once again, thank you so much for the opportunity to talk to your hub and tell you a little bit about some of the activities we're funding.
Great, thank you so much. I'm going to stop recording here.